Hi everyone, welcome back. So what I'm going to do in this clip is I'm going to discuss the last part of perturbation theory, which will be an application to a periodic perturbation. Periodic perturbations, they are widely used in optics and light matter interaction because they are a good way of modeling a weak time-dependent electromagnetic field. So this is what we're going to see next in a whiteboard derivation in this lecture. Okay, so far we have discussed constant perturbations, and what we're going to see now is a harmonic perturbation. So the key idea is that this perturbation is time varying, and some of the easiest treatments that you can give, especially in the context of light matter interaction, is we're going to have a perturbation varying in time. So far, we had a constant perturbation. And now we're going to have a look at a harmonic perturbation. And this is quite useful if you want to model light matter interaction. And you can consider the atom to be an electric dipole. And this is, in fact, very used in the dipole approximation. So this means that what we're going to have is we're going to have a model of an atom in a monochromatic laser. And this means that the electric field of the laser is of this form, whereby omega is the angular frequency of the radiation, and E naught is the field amplitude. As we can clearly see, this is a function of time. So what we would like to do next is we would like to write the interaction Hamiltonian for this system. We have seen that when we have perturbation theory, we have H naught, which is the unperturbed Hamiltonian, plus the perturbation. And the interaction Hamiltonian for this, we have seen a lot already. We mentioned it in some context. We're going to write it as V minus E, scalar product with G, whereby G is dipole moment, and our V then is an operator, okay? So our V is Hi cos omega t, coming from the field. So this is an operator. Let me put heads on those to make it clear. This is an operator that is going to tell you more information about the quantum description of the interaction. For instance, if you have transition rules, if you have all these kinds of things. What is interesting for us now is that we have a sinusoidal perturbation, and we are going to solve that. It is for us more interesting to write it in a slightly more general way. So we are going to use this expression whereby this is the creation operator. No, this is the annihilation operator, and this is the creation operator. So if you have that A is a real symmetric matrix that is going to reduce to the expression which you have here above. This is more general. So let me write just for clarity. Creation operator. No, here, I always get it confused. This is annihilation operator, and this is the creation operator. Okay, so what we're going to do is we're going to assume that this perturbation is switched on at t equals 0, and that prior to that, and at t equals 0, the system is prepared in the state phi j of the unperturbed Hamiltonian. So these are this is an eigenstate of the unperturbed Hamiltonian with energy Ej. Eigenstate of H naught, which is our unperturbed Hamiltonian, and the energy associated with it is Ej. Okay, so after and when this was switched on, our Hamiltonian will be H naught, so this is H, which is the total one, plus I omega t plus A dagger E minus I omega t. So we have the perturbation and we have H naught, and we're going to use our results derived in the previous session. So we want to calculate the coefficients of the state CMT phi m. Don't forget that we'll be dealing with interaction picture, and we want to calculate this to first order. So up to the first order perturbation theory, CMT will be CM 0th order plus CM 1t, whereby this is what you obtain with the first order expansion, with the 0th order expansion in lambda, and this with the first order expansion in lambda. So as before, CM naught is determined by the initial conditions, which are that psi at t equals 0 is phi j, something we specified, make this psi t, so that we know. This means then that CM naught, remember the derivative of CM naught is 0, so is something constant, is delta mj, where this is the Kronecker delta. Now, how about the first order term? First order term is given by Cm1 of tau, whereby tau is where when we perform the measurement, 1 over IH bar, integral from 0 to tau, dt Vmj t e to the power I omega mj t. And what we would like to do is we have this expression here for V. So we need to calculate our matrix elements between the eigenstate, between our eigenstate phi m, which is our final eigenstate, and the eigenstate phi j. So just to remember, this is a transition coupling phi j, which is the initial state, to phi m, and we need to calculate, we need the matrix element phi m vt phi j, right? So it's clear what we have to calculate, and we're going to have then a and a dagger, and we have these integrals. So a and a dagger are going to depend on how these states are defined. They are operators. They're going to be sandwiched by the final and the initial states, but we do have the expression for Vt here on top. Let me put a t here so that we know. And copy. So I'm moving it here so that we know what we would like to achieve. Okay, so let's calculate this phi m vt phi j, this matrix element. This is going to give me phi m a phi j e to the power I omega t plus phi m a dagger phi j e minus I omega t. So I'm going to call these things here a mj, and I'm going to call this a dagger mj. Remember that we don't know how these operators are acting upon these things, so we'll keep it vague because this is going to depend pretty much on the state of your system, how it's going to behave. If you have atomic states, molecular states, the parities, etc., if you're using ladder operators. So I'm not going to go into detail. We're interested in the temporal form of this whole thing. And this also we can write as a star jm. Remember how a and a dagger are connected. If you have an operator a, the a dagger operator, like the adjoint operator, is going to be, if you're looking at it as a like in terms of a matrix or in form of a matrix, you're going to transpose and take the complex conjugate of the matrix element. So that's why I'm writing it in this way. So we're ready to get this and insert into C1 M tau. So let's do that. So what we're going to do then is we're going to insert this into CM1 tau, which is the expression up to first order perturbation theory. So we're going to find that CM1 tau is going to be 1 over IH bar A MJ integral from 0 to tau DTE I omega MJ plus omega T plus A star JM integral from 0 to tau TT E I omega MJ minus omega T. So you see what is happening. You have here some integral in which we consider the energy difference between the lower and upper level plus the angular frequency. And here we have the Bohr frequency associated also with the difference between the lower and the upper level minus the angular frequency of the perturbation. So we're going to integrate this. And what we find then is that this is going to give me AMJ divided by H bar. Now, this integral is going to be the first integral, which is, I'll put the I here so that you can see. This is going to be EI omega MJ plus omega T divided by I omega MJ plus omega. This T here is going to go from 0 to tau plus A star JM. And here we're going to have EI omega MJ minus omega T, I omega MJ minus omega, going also from 0 to tau. So you see what I've done? I've integrated these two exponentials and I am writing them in a way that we're going then to calculate this perturbation. Here I forgot the IH bar. Okay. So pretty much let's look at these definite integrals. If you multiply these two i's here, you get -1. So for the first one, I'm going to have let me mark this. So call this star, call this double star. So once I do all the cleaning up, this is going to be A MJ divided by I times I, so this is -1 H bar. And you still have omega MJ plus omega. and this is going to be EI omega mj plus omega tau minus 1. So A mj divided by h bar omega mj plus omega, and here you're going to have 1 minus EI omega mj plus omega tau. Okay, similarly, we'll find that this other integral, which I called double star, is going to be A star Jm divided by h bar 1 minus EI omega mj minus omega tau divided by omega mj minus omega. Okay, so we're getting there. And what you can see is that you can do some rearrangement when you add up these two things. And you'll be able to write this as a sink. So this is a good exercise to try to show at home. But I'm gonna show you quickly how this goes. And what to do in the end is you're going to have an expression which is going to tell you that Cm1 tau is AMJ divided by h bar 2I pi e to the power I omega mj plus omega tau over 2 multiplied by sinc omega mj plus omega tau over 2 plus AJM star divided by h bar 2I pi e I omega mj minus omega tau over 2 sinc, put it like this, multiply here down, is nicer. Sinc omega mj minus omega tau over 2. I'm not going to do this. We have discussed this in detail for the constant perturbation. So if you want to have a look, details, previous clip on constant perturbation. And you'll be able to see there. I do recommend, but one thing that you can see is that we have once more sinc functions. If you remember, sinc functions, they look like this. They're highly peaked. They have some kind of width. And the difference is before we have a sinc function centered at omega equals 0, which would mean that you would be coupling omega mj equals 0, meaning that the energies of the states that you would be coupling would have to be the same. You only couple degenerate states via your perturbation. Now it's kind of a bit different. So this is just a sketch of the sinc function. So this is omega, and this is sync omega. So you know how it looks. And what we have is now we have these two. We have first sync omega mj plus omega tau over 2. And then we have sync omega mj minus omega tau over 2. And if you remember, in the long time limit, we had that this sync omega mj plus omega tau over 2 was proportional to delta omega mj plus omega. And now we have also that sync omega mj minus omega tau over 2 is proportional to delta omega mj minus omega. So this means that these coefficients, so it is our main conclusion. This means that in this limit, Cm1, which is the first order transition coefficient, is going to be non-zero if only if omega mj is equal to omega, or omega mj is equal to minus omega. Can you see this is interesting? Because this means that only in this case you can have some transition from the initial state to the final state. So if you recall, you had your initial state, phi j, with energy Ej. Your final state is phi m with energy Em. And we have that this Bohr frequency W omega j is Em minus Ej divided by h bar, correct? So we can see that if omega j is equal to omega, this means, so let's see the case omega mj equals omega. This means that Em minus Ej divided by h bar is equal to omega. So strictly speaking, we can conclude that Em is equal to Ej plus h bar omega. And this is quite interesting because you can see that this sinusoidal harmonic perturbation is allowing a transition from Em, from Ej to Em by absorbing something which has a frequency or energy h bar omega. So if you want to think about in terms of a one photon transition, you would have here a state with energy Ej. Here you have a state with energy Em, and you couple this by having a resonant photon. So this would be then h bar omega. It would absorb and go one up. So this is an absorption, it's a resonant if you want. One photon absorption process. Why resonant? Because I'm imposing that this frequency here has to be equal to this energy difference here multiplied by h bar. Now, if we go for the other case, which was this one, what do we see? We see that if minus omega is equal to Em minus Ej divided by h bar, we'll find that Em, which is your final state, is going to be equal to Ej minus h bar omega. So this means that Em is 1 unit of h bar omega lower than Ej. So before you went 1 unit up, now you have to go 1 unit down. So this means that you can release one photon and then go down. So you're going to have some kind of emission. And this is interesting because you can see that before you would go from Ea, Ej to Em, where you would have this h bar omega. And now you go from one to the other, but you release one h bar omega. So this is quite nice because first order perturbation theory, and this is a big, big please note. First order perturbation theory predicts that light energy can only be absorbed by an atom or a system, depending on what you're using here, in units of h bar omega. And this is a photon. So it was obtained even without a fully quantum mechanical treatment of light. It was obtained just using one first order perturbation theory. So similarly to the other case where we had a constant perturbation, we can also derive Fermi's golden rule, and we're going to do that. But what you should note is that, for instance, here you have what we call emission. Here you have absorption. And if you compare to the constant perturbation, in a constant perturbation, what you had is you always had states of the same energy being coupled. And now either the final and initial states or either the initial state is one energy down with regard to the final state, or 1 unit of h bar up. So they are always separated by a unit of h bar omega, where omega is the angular frequency of the radiation you're putting in. So this is a quite powerful result, and it's quite interesting as well to see. And we're going to talk about Fermi's golden rule here. And it can be derived in pretty much the same way we have done for the constant perturbation. So I'm not going to go into detail, but what we can see is that we're going to have what we call absorption rate. So the rate that this system is going to absorb one photon to go from one state to the other. So gamma 1 to perturbation theory of it going from state phi j to state phi m as a function of tau, which is the time for which this has been measured, can be written like this: a mj square delta e m minus ej minus h bar omega. So this is the rate with which the system is going to absorb a single photon. And you can see here the coupling plays a big role. So square of the coupling. So this is going to be proportional to the field strength. So we're going to have something proportional to the field intensity. And you have a delta, which is guaranteeing that in the long time limit, this is going to be a resonant process. So to go up and down, you would have to have a photon whose angular frequency is equal to the Bohr frequency between lower and upper states. Okay, and this is also constant. But bear in mind, this is first order perturbation theory. And for emission, we have a similar situation, but we know that one photon was emitted and your system pretty much went down the ladder. So if it was in an initial state phi j with energy ej, it emitted one photon h bar omega, and it went down to a final state whose energy is lower. So the emission rate, let me put here rate so that you know, using Fermi's golden rule, or proceeding the very same way from what we have done, we're going to find that this is going to be 2 pi divided by h bar a star jm delta e m minus ej plus h bar omega. So in this expression now, don't forget the square. And one thing that we have considered here, and to which this rate that we have derived in perturbation theory refers to, is that this is a process in which one photon is involved, but this is also called stimulated emission, because this is the emission of a photon in the presence of an electromagnetic field. So this field is stimulating this emission, is making it occur, because it is as if you add one photon more to a specific mode of your external electromagnetic field. Now, we are going to see that this specific emission rate can be written in a bit of a different way. And to do that, let's do the following. Let's consider that AJM star modulo square is equal to AJM modulo square, which is clear because if you have the modulo square of the complex conjugate of something, that is going to be the modulo square of that thing which you conjugated. And we can also use the fact that, so we are using that delta EM minus EJ plus H bar omega is equal to delta EJ minus EM minus h bar omega. Here we have just used that delta x is equal to delta minus x, which is a property of delta functions. And what happens in the end is that this gives you a rate which is this emission rate to the first order perturbation theory, 2 pi divided by h bar. Let me see the rest. A jm square delta ej minus em minus h bar omega. Now note that if I swap the indices, I'm going to get delta mj1 2 pi divided by h bar omega amj square delta em minus ej minus h bar omega. Can you see what this is? This is this expression that we had for the absorption rate. So let me write this nicely. It's a bit strange. Minus h bar omega. And this is formally the same as the absorption rate. And the reason for this is what we call principle of detailed balancing, which means that the rate of stimulated emission from K to J is equal to the rate of absorption from J to K. So rate of stimulated emission from, here we don't have K, we have M. So from phi M to phi J is equal to the rate of absorption from phi J to phi M. And that's why we needed to show that if you swap the indices and you do some manipulations, you get the same expression, because you are going to have that the rate of a process occurring is equal to the rate of the opposite process occurring. So this is something very useful if you're dealing with systems in equilibrium, and it's widely used when you're doing computations. So I hope you enjoyed time-dependent perturbation theory. That's what we're going to discuss, at least asynchronously so far. And in the next clip, we're going to move to the final topic of this course, which is related to the dynamics of open quantum systems. And to know how to treat open quantum systems is extremely important if you are dealing with systems for which it is not viable to solve the time-dependent Schrodinger equation, because you have many degrees of freedom, because you have classical randomness, or because it is just impossible to define what would be your system and what would be your environment. So I hope you enjoy this topic and that you are having fun learning quantum mechanics.